Okay, let's talk about determinants. So the determinant is an operation that we apply to square matrices. Specifically, the determinant is a scalar we associate to a square matrix. So if we're dealing with a matrix that is not square, so maybe like a 3 by 5 matrix, that matrix does not have a determinant. But if we're working with a matrix that is square, like a 5 by 5 matrix, that 5 by 5 matrix does have a determinant, and the determinant is a scalar value. Now, I want to issue a word of warning here. Determinants can be used for many things, but they often don't need to be used for things. So determinants are one of the most overused operations in linear algebra. So I want us to keep this in mind as we discuss our formulas and applications of this concept. Sometimes we actually do need determinants, but many times we don't. Okay, so let's start by introducing some notation that will make the definition of the determinant more accessible. The first notion I'd like to bring up is the notion of the ij submatrix of a matrix A. The ij submatrix of a matrix A is denoted by A sub ij, and this is the matrix obtained by deleting the ith row and the jth column from the matrix. So here on the left, we have an example where our matrix A is a 4 by 4 matrix. So to find its submatrices, we need to declare which row we want to delete and which column we want to delete. So on the right here, we're looking at the 2-1 submatrix. The 2-1 submatrix is obtained by deleting the second row of our matrix and then deleting the first column of our matrix. The 4-3 submatrix is constructed similarly, except now we're deleting the fourth row of our matrix and the third column of our matrix. And the 3-2 submatrix is also defined similarly. Now we're deleting the third row of our matrix and the second column of our matrix. So one thing to pay attention to in this example is that A is a 4 by 4 matrix, and every time we delete one row and one column, we're reducing the number of rows by 1, and we're reducing the number of columns by 1. So each one of the ij submatrices for this example is a 3 by 3 matrix. So the ij submatrices are smaller matrices sitting inside of the larger matrix. Okay, so this is the only notation we really need to define the notion of a determinant of an arbitrarily sized matrix. Now, one of the issues or one of the problems with the definition of a determinant is that it's actually somewhat complicated in the sense that the definition is recursive. So to properly define the notion of a determinant, we need to first define what it means to take the determinant of a 1 by 1 matrix. Then we will use this definition to define the determinant of a 2 by 2 matrix. Then we will use the definition of a 2 by 2 to define the definition of a 3 by 3. The 3 by 3 definition will be used to define a 4 by 4, and so on. So it all starts with the definition of the determinant of a 1 by 1 matrix. So a 1 by 1 matrix is nothing other than just a scalar sitting inside of a 1 by 1 grid. The determinant of this scalar, or of this 1 by 1 matrix, is simply that scalar. Okay, so it's very easy to take a determinant of a 1 by 1 matrix. What about a larger matrix? So here is the definition of the determinant of an n by n matrix. So the determinant of an n by n matrix is defined as follows. So the notation we use is det A, and this is equal to a sum that has n terms. So here we're taking the sum from k equals 1 to n of -1 to the k plus 1 multiplied by the k1 entry of our matrix multiplied by the determinant of the k1 submatrix of our matrix. Now, at first glance, it might look like there's an issue here because we're using the concept of a determinant to define the concept of a determinant. But if we look a little closer, we realize there's actually not an issue with this. Because on the right here, we're taking the determinant of a submatrix of a larger matrix. So if the matrix we're taking a determinant of is a 4x4, well, according to the definition, we should end up with 4 terms, and each one of these 4 terms uses the formula for the determinant of a 3x3. So for a 4x4, this determinant is a 3x3, and each one of those determinants is used to build the determinant of a 4x4. So there isn't any circular logic here. There's also notation that is commonly used here. So the notation det of A is what I like to call descriptive notation. When we write det of A, we're clearly taking a determinant of A. But it's also very common to see this sort of absolute value notation. If we enclose the symbol for our matrix in vertical bars, we're not referring to the absolute value of anything. We're referring to the determinant of this matrix. Okay, so let's now use this definition to find the formula for the determinant of a generic 2x2 matrix. So here we have a general 2x2 matrix, and the entries in the columns here are the numbers A, C, B, and D. So according to our formula, the determinant of this matrix should have exactly 2 terms, and each one of these 2 terms should involve the determinant of a submatrix of this 2x2 matrix, which will be a 1x1 matrix. So by definition, we're taking the sum from k equals 1 to 2 of -1 to the k plus 1 multiplied by the k1 entry of our matrix multiplied by the determinant of the k1 submatrix of our matrix. So let's actually write down these 2 terms explicitly. So when k is equal to 1, the first term here should be -1 to the 1 plus 1 multiplied by the 1, 1 entry of our matrix multiplied by the determinant of the 1, 1 submatrix of our matrix. Then our next term needs to be when k equals 2, and when k equals 2, we're dealing with -1 to the 2 plus 1 multiplied by the 2, 1 entry of our matrix multiplied by the determinant of the 2, 1 submatrix of our matrix. So here we've counted our k's and we've listed our 2 terms for the determinant. But now we can interpret each part of these 2 terms. So in the first term here, we're looking at -1 to the 1 plus 1. That's -1 squared, which is equal to 1. So we're weighing this term positively. The 1, 1 entry of our original matrix is the number in the upper left-hand corner, which we're just calling A. And then the 1, 1 submatrix of our 2x2 matrix is obtained by deleting the first row and the first column of our matrix. So the first term in our determinant here should be the number A, which is in the 1, 1 entry, multiplied by the determinant of whatever's left over in our matrix when we delete the first row and the first column. Then when we proceed to the second term, we're looking at -1 to the 2 plus 1, which is -1 cubed, which is -1. So we're weighing this term negatively. Then we're looking at the 2, 1 entry inside of our matrix, which is the number D in the bottom right-hand corner of this 2x2 matrix. Or sorry, which is actually, no, sorry, the 2, 1 entry is actually the number C in the bottom left-hand corner of this matrix. Then we're multiplying by the determinant of the 2, 1 submatrix, which is obtained by deleting the second row and the first column of our 2x2. So now our 2 terms are a bit more clear. Our first term is going to be the 1, 1 entry multiplied by the determinant of what's left over when we delete the first row and first column. And then we're subtracting off the 2, 1 entry, which is this number C, multiplied by the determinant of whatever's left over when we delete the second row and the first column of our matrix. And of course, both of these determinants are determinants of 1x1 matrices, which are just the number sitting inside of these matrices. So the first term here should be A times D, and the second term here is minus B times C. So that's the formula for a generic 2 by 2 determinant. People often remember this as taking the product of the diagonal of the entries inside of this 2 by 2 matrix, and then subtracting off the product of the other two terms inside of the matrix. So 2 by 2 determinants are actually pretty simple to both remember and calculate. Okay, so now let's apply the formula for the determinant of a 3 by 3 matrix. So to find the determinant of a generic 3 by 3 matrix, we should be able to just follow the formula like we did before. Two key things to remember are that since this is a 3 by 3 matrix, the formula says we should have 3 terms. And the second thing to remember is that each one of those 3 terms should involve the determinant of a 2 by 2 matrix. And we just found the formula for the determinant of a 2 by 2 matrix on the previous slide. Okay, so our generic 3 by 3 matrix is represented as follows. We're using different letters for each column of this matrix. So the first column are the numbers A1, A2, A3. The second column consists of the numbers B1, B2, B3. And the third column consists of the numbers C1, C2, C3. So let's now apply the formula. By definition, we're looking at the sum from k equals 1 to 3 of -1 to the k plus 1 multiplied by the k1 entry of the matrix multiplied by the determinant of the k1 submatrix. When we plug in k equals 1, 2, and 3, we get our 3 terms. The first term will be -1 to the 1 plus 1 times the 1, 1 entry of the matrix times the determinant of the 1, 1 submatrix. Then when k equals 2, we're looking at -1 to the 2 plus 1 multiplied by the 2, 1 entry inside of the matrix multiplied by the determinant of the 2, 1 submatrix of the original matrix. Then the third term is when k equals 3, and we're looking at -1 to the 3 plus 1 multiplied by the 3, 1 entry of the original matrix multiplied by the determinant of the 3, 1 submatrix of the original matrix. And we can now look at these terms a little more closely and actually fill in what they're equal to. In the first term, -1 to the 1 plus 1 is -1 squared, which is 1, meaning we're weighing this term positively. The 1, 1 entry inside of our 3 by 3 here is the number a sub 1. And the 1, 1 submatrix is obtained by deleting the first row and the first column of our matrix. So now the first term is a sub 1, the first entry in the first column, multiplied by the determinant of whatever's left over when we delete the first row and the first column of the original matrix. Then when we move to the second term, we're looking at -1 to the 2 plus 1, which is -1 cubed, which is negative, so we're weighing this second term negatively. Then we're multiplying by the 2, 1 entry inside of our matrix. That's exactly the second entry in the first column, which we're calling a sub 2 here. Then we delete the second row in the first column and take a determinant of whatever's left over. Again, that'll be a determinant of a 2 by 2 matrix. Then for the last term, we're looking at -1 to the 3 plus 1, which is -1 to the fourth, which is plus 1, so the third term is weighed positively. Then we're looking at the 3, 1 entry of the matrix, which is the third entry in the first column, which we're calling a sub 3. Then we're multiplying by the determinant of the 3, 1 submatrix, which is obtained by deleting the third row and the first column of the original matrix. Again, we'll be left with the determinant of a 2 by 2. So when all said and done, as promised, we're looking at 3 terms for the determinant of this 3 by 3. Each one of these 3 terms is a choice of one of the entries in the first column multiplied by plus or minus 1, depending on its location. Then we delete a row and a column and take a determinant of whatever's left over. So we end up with 3 terms where each term depends on the formula for the determinant of a 2 by 2 matrix. And the idea is that 2 by 2 determinants are not difficult to calculate. So once we have this formula, we can quickly calculate the determinant of our 3 by 3 matrix. Okay, so one of the issues now is that this formula is not horribly difficult for 2 by 2s. It's a little bit more complicated for 3 by 3s. But as soon as we get to matrices of size 4, 5, 6, or even higher, we end up with kind of a mess. Imagine taking the determinant of a 5 by 5 matrix. Well, according to the formula, that 5 by 5 determinant will have 4 terms, and each one of those, the 5 by 5 will have 5 terms. Each one of those 5 terms will depend on the formula for a 4 by 4 determinant, and each one of those 5 4 by 4 determinants will have 4 terms, each of which depends on the formula for a 3 by 3 determinant. So calculating a determinant of a 5 by 5 matrix by hand like this requires a lot of effort, and things get out of hand pretty quickly. So we will now want to sort of turn our attention to introducing notation and techniques that make these calculations more manageable. The first useful piece of notation is the notion of the ij minor of a matrix. The ij minor of a matrix A is the determinant of the ij submatrix of the original matrix. The ij minor is usually denoted by m sub ij. So m sub ij is the determinant of the ij submatrix of the original matrix. The ij cofactor is the ij minor, so the determinant of the ij submatrix, scaled by either plus or minus 1. And the way we construct the scale is by looking at the number -1 to the I plus j. So the ij minor is the determinant of the ij submatrix, and the ij cofactor is -1 to the I plus j multiplied by the ij minor. And one immediate application of this idea is that cofactors make the formula for determinants nicer. In the formula for the determinant, what we're doing is we're plucking out the k1 entries of the matrix as k runs from 1 to n. Then we multiply by -1 to the k plus 1 multiplied by the determinant of the k1 submatrix. That term is all lumped into the cofactor. So now the determinant is simply k equals 1 to n of the k1 entry multiplied by the k1 cofactor. So here what we're looking at are all 9 possible cofactors of a generic 3 by 3 matrix. So since a 3 by 3 matrix has 9 entries, it has 9 cofactors. For example, in the upper left-hand corner here, we're looking at the formula for the 1,1 cofactor of a generic 3 by 3 matrix. According to the definition, to take the 1,1 cofactor of a matrix, we should be looking at the factor -1 to the 1 plus 1, which ends up being -1 squared, which is plus 1. Then we delete the first row and the first column of the matrix and take a determinant of whatever's left over. If we move to the right one here, we're looking at the formula for the 1,2 cofactor, which is defined as -1 to the 1 plus 2 multiplied by the determinant of whatever's left over when we delete the first row and the second column of our matrix. If we move like right one and down one over here, we're looking at the formula for the 2,3 cofactor of a 3 by 3, which by definition is -1 to the 2 plus 3 multiplied by the determinant of whatever's left over when we remove the second row and we remove the third column from the matrix. So when all said and done, for a generic 3 by 3, we can take 9 different cofactors of that matrix.